Welcome to this presentation where we continue to talk about content contained in the book Introduction to Nonlinear Control. And in particular, in this video, we are going to talk about the content contained in Chapter 10 and talk about sliding mode control. And we will go through one particular example to highlight the main steps of basic sliding mode controller design. What we consider here are systems of the following form: x dot is equal to f of x, comma u, comma delta, and an output y is equal to h of x. Here, as before, x denotes the state, u denotes the input, y the output, and now the new component for this chapter is an unknown disturbance delta, which can be a function of the time and of the state x. And our goal is to stabilize the origin of our system despite the presence of this disturbance delta. So that's what I'm going to do based on one particular example. But first, before we can get there, we need to discuss the concept of finite time stability. And that's kind of a stronger assumption than asymptotic stability. So let's just quickly recall how we've defined asymptotic stability. Well, asymptotic stability for a system x dot is equal to f of x with equilibrium at the origin was defined through stability and attractivity, where stability means that if we start close to the equilibrium, so if x of 0 is less than delta, then that needs to imply that the corresponding solution stays within an epsilon neighborhood for all times t bigger than 0. And attractivity then on top of that means that, well, if we start close to the equilibrium, and then our solution asymptotically needs to converge to 0. A different representation for that is through Lyapunov functions, which we've also seen, meaning we can characterize the asymptotic stability properties of an equilibrium through a Lyapunov function. Lyapunov function v being a continuously differentiable function with these additional functions needed for the definition, k-infinity functions and a positive definite function, so that we have radially unboundedness of the Lyapunov function captured here, and this degrees condition ensuring that the trajectories v evaluated along trajectories is strictly monotonically decreasing until we asymptotically reach the origin. Okay, and we can extend that asymptotic stability now to a stricter condition, namely finite time stability. How is that defined? Well, we take again a system of the form x dot is equal to f of x, again with equilibrium at the origin. Then we say that the origin is globally finite time stable if we can find a so-called settling function or settling time function t mapping from Rn, but not including the origin to the positive real numbers. And the following two properties have to be satisfied, essentially capturing stability and finite time convergence, so the extensions of, again, stability and attractivity. So stability is still the same, meaning for all epsilon bigger than 0, we need to be able to find the delta such that if we start in the delta neighborhood, our solution is going to stay in the epsilon neighborhood for all t in this interval from 0 to t of x, so depending on our settling function t and on the initial condition. And then in addition to that, we need finite time convergence, meaning, since we here look at global properties for all x excluding the origin, the solution needs to be defined on this interval 0 to t of x0. X of t needs to be unequal to 0 for all t in t of x0, but then if we let t go to this value t of x0, then x of t needs to converge to 0. So that's just a definition, but as before, we can also characterize that through corresponding Lyapunov function. We need to make slight adjustments also over here. So in this case, the properties the Lyapunov function needs to satisfy is that v needs to be now just a continuous function from Rn to the positive real numbers, and only needs to be continuously differentiable on Rn, excluding the origin. So we have to exclude the origin here with respect to differentiability. We still have the same assumptions in terms of radially unboundedness. And now what is changing here is the right-hand side, the decrease condition. Instead of capturing that through a positive definite function, now we have the condition that this needs to be, the decrease needs to be written in terms of constant times the square root of the Lyapunov function. And then we can conclude global finite time stability from this Lyapunov function, and this result up here additionally provides us an upper bound for the settling time through this upper bound here, the k infinity function alpha 2. Okay, so how can we use this now for sliding mode controller design, or is there actually an example of a function where we have finite time stability? So just as a quick example, before we get to the actual content of sliding mode control, we can consider x dot is equal to minus the sine of x, and then the third root of x squared. With that, it can be shown that the solution is of the following form here. And by arguing then on the sign of the derivative of this function f of x of t here, we can conclude that we have an asymptotically stable origin here. So the origin is asymptotically stable, and moreover, by directly looking at the solution here, we also get the time when x of t is equal to 0, and through a Lyapunov characterization, it can be shown that this function v of x here is a Lyapunov function characterizing finite time stability, which then also allows us to calculate the settling time. And that's visualized on the right. So we see here on the right the convergence of different trajectories corresponding to different initial conditions. And then on the bottom, the settling time, symmetric with respect to the origin, and then strictly monotonically increasing if we go further away from the origin. Okay, but yeah, this is a good example to check if you understand finite time stability, and if you can then make the corresponding calculations to get a corresponding finite time Lyapunov function. But with that, we then have the tools to go back to sliding mode controller designs and to outline the main steps for a sliding mode controller here. And as mentioned before, we are going to look at a particular example, namely here x dot is equal to x cubed plus z, z dot is equal to u plus delta. So we have our disturbance popping up over here. And yeah, as before, the function delta can be a function of the time and here of the state x and z. And the assumption we need to make is that we know an upper bound on this disturbance. So this function delta can be a discontinuous function, but can behave in weird ways. But what we need is that we have this bound available here. Then what we want to achieve now is exponential stability, or let's say asymptotic stability of the origin of the X subsystem. So that would be mean stabilizing the output y is equal to x, for example, which means what we want to achieve is that our subsystem x dot essentially behaves like this, that it looks like x dot is equal to minus x. And that should be the case for all bounded disturbances. We could also add minus 2x here, but this guarantees this system here is exponentially stable or asymptotically stable. So that's what we want to achieve, but we can also change the convergence rate here. Well, so this equation here is equivalent to the desired behavior x dot plus x is equal to 0. And if we plug in the definition of x dot, then we end up with this expression down here. Now, of course, in general, this won't be equal to 0, so we can define a new variable sigma as this left-hand side here, which is then just a function of the state x and z, and we can introduce this function here, which will be used as a Lyapunov function later on. But at this stage, it's just a candidate Lyapunov function for which we want to design a controller such that a certain decrease is satisfied. All right, as a next step, what we're going to do is take the derivative of v with respect to the time, simply giving us sigma times sigma naught, and we can plug in the expression for we can calculate the derivative of sigma simply by taking the derivative of this equation, providing us this equation up here. We need to replace x dot, z dot, and x dot, which we can do by using the information here of our dynamical system, and we end up with this long expression here for v dot. To simplify that expression, we can cancel the known terms, meaning we introduce or define u in the following form, canceling the particular terms here, and here, and here, and here, just leaving us with this unknown term, and by keeping the degree of freedom here in terms of a new variable v. If we plug that in, well, then we simply are left with this expression here, which we want to ensure that this is strictly decreasing and satisfies the conditions of Lyapunov function characterizing finite time stability. Okay, so how do we proceed? Well, we still have that degree of freedom in the function v, so we define that as minus a constant times the sine of sigma, and we plug that in again into our function v dot of sigma. We can simplify that term simply by getting minus rho times the absolute value of sigma, plus a term depending on our unknown disturbance delta. So this term we like, that's a decrease we can use later on. This term here we need to estimate, so we have delta here, delta in this expression here. We know a bound on delta, which means we can estimate it through this constant L times the absolute value of sigma, which then provides us this final result here in terms of the decrease condition. Now, let's remember what we still haven't defined yet. So we said that the rho is a constant bigger than 0. So we can define that in a particular way, where we again leave kappa as a degree of freedom, and then the previous expression simplifies to v dot of sigma is less or equal to minus kappa over the square root of t, square root of 2 times the absolute value of sigma, which allows us to capture this in terms of the function v, and provides us with now a certificate for finite time stability of sigma. Okay, and if we now go one step back, so the degree of freedom in our system is actually u. So what does it mean in terms of u? Well, u needs to be defined in this particular way here. So simply by collecting the terms and the simplifications we've done along the way, we end up with this input u here, which only depends on known terms, meaning it is in particular independent of the disturbance. So this is really something we are able to implement. Okay, now we've done the main steps. We just have to collect a couple of results. So what we get here, or what we started with, was this dynamical system. We have constructed the control law here, and now we can simulate it for just to see the performance for some particular disturbances. So one disturbance would here be sine t, the other one just another disturbance depending on the sign of cosine and sine. And then we see this particular convergence, or the convergence properties here, and the corresponding input corresponding to the first delta and the second delta. And what we observe is that, as we would expect, hopefully, that sigma converges to 0 in finite time. And so we see here that sigma starts negative and then converges to 0 in finite time. Similarly over here, and it's highlighted at what time 0 is reached. Once that's achieved, then we observe that our states x and z asymptotically converge to the origin. So first we have the finite time convergence to 0, and then the asymptotic convergence of x and z. And well, we don't really see the impact of these different disturbances delta here. We would not be able to, or just by inspecting it here, we are not able to see which disturbance corresponds to that, but we see this chattering phenomenon here corresponding to the sine function here in the control law u, leading to this chattering in the feedback law. Yeah, and so and this particular only occurs because we can only solve the ordinary differential equation numerically, so we will never exactly achieve sigma equal to 0, and that's why we have this chattering. Just zoomed in here, so again, what do we observe? So here is This shows the sliding surface where sigma is equal to 0. So we see this convergence to that sliding surface, and then once we are there, we have this chattering to the left, to the right. And then once we reach that, then that's the time when we can observe this asymptotic convergence, which is kind of similar to the solution properties we observe in backstepping or forwarding. Okay, and that concludes the content I want to cover here on sliding mode control. And then in the next talk, I will talk about parts of chapter 11 on adaptive control.